The next 2 weeks, we're going to talk about derivatives. You probably thought you've heard all you wanted to hear about derivatives and calculus, and how could there be 2 more weeks worth of stuff? But there's some very interesting methods, many of which you probably haven't seen before, that can be very powerful and useful, not just in optimization, but in many computational applications where you need derivatives, like in solving ODEs or doing various types of sensitivity analyses. Or uncertainty quantification, there's often scenarios where we would like to have derivatives of a function. And it's no different here in optimization. We're going to make good use of derivatives when we can. Today, we'll start with some methods that you probably are already familiar with, do some review, and then we'll start getting into some new methods next time. So this is a little bit out of order of the book. We'll come back to constrained optimization after we discuss derivatives. I'm going to share my screen. And there we go. Okay, so today, I guess the main topic is finite differencing, but we'll have a little bit of preliminaries before that, just by way of review. Okay, so first let's review what it is we're really interested in. We've already seen the gradient, right? So if I've got some function, let's say f of x, and in general, x is a vector and f is a vector. For unconstrained optimization, we just had an objective, so f was a scalar. But pretty soon we're going to be doing constraints, so we're going to have many outputs. So normally we call G constraints and f the objective, but for our purposes, to keep things simpler here, we're just going to call x inputs, f outputs. You can forget about optimization for the time being. And it could be that f contains an objective and many constraints, or it could be some dynamic simulation where we want derivatives. It doesn't matter. It's just that we've got nx inputs and nf outputs in general. Now, in the case that if f was a scalar, meaning nf equals 1, that's the case we already saw. So we have a gradient vector, right? The gradient of f, there's only one f, so we just take the partial with respect to each component of x all the way up to xn, or let's say we've been calling it nx, I guess. And I put a transpose because we normally will write vectors as column vectors. So here everything is a row, so it should be the transpose to indicate it's a column. But in the general case, f is not a scalar. So if nf is greater than 1, then we have what's called the Jacobian, right? The Jacobian of x, and it is a matrix. So it's a matrix like this, where this is the partial of f1 with respect to x1 all the way to the partial of f1 with respect to nx. So this row, for example, is the gradient of just f1, but then I've got f2, right? Oops, with respect to x1, all the way f2 with respect to nx, and I'm gonna make this a little bigger. Go down to f and f with respect to x1 to f and f, x and x. Okay, so this is in general, non-square matrix. It's an nf by nx sized matrix. So often we have different numbers of outputs and inputs. In the optimization context, that would be like our objective and constraints are a different number than the design variables. Those are independent things. And sometimes we like to write this in index notation. The ijth component of that matrix would be the partial of fi with respect to xj. Okay, so that's a Jacobian. And so you can see there's lots of derivatives. We're going to be talking about first derivatives here. These are things that we want to be able to compute. All right, so let's just do an example. This is actually example 6.1 in the book, but just to review real quick. Let's say we've got 2 inputs, 2 outputs. So we're going to do the function looks like this. F of x has two outputs, so I'm just going to write it this way. Put it as two entries in this column vector. First one looks like this, x1, x2 plus sine x1. That's f1. And the second entry in f, the second output, is x1, x2 plus x2 squared. So we want to get the Jacobian. The derivative of f with respect to x, that's going to be a matrix of what size? It's going to be 2 by 2, right? Because I have two outputs, two inputs. And so this first entry here, that's going to be the partial of f1, this row, with respect to x1. And this is a partial derivative, so there's no x1 here, that goes away. The partial of this with respect to x1 is just x2, right? Oh, you know what? Actually, if I want to follow the example, what I said was correct, but the example actually has an x1 in it. So we do that again. The partial with respect to x1 is x2, and then the derivative of this term with respect to x1 is cosine x1. Okay, so now the second entry, this is still the partial of f1, but with respect to x2. And x2 doesn't appear here, only here, so I just get x1. Second row is now the partial of f2 with respect to x1 and the partial of f2 with respect to x2. So the partial with respect to x1 just gives me an x2, and the partial with respect to x2 gives me x1 plus 2x2. Sorry, it's getting too cramped there. Okay, so that's symbolically, of course, we're going to be doing these numerically. So this would be evaluated at, say, some point. Let's say the point was x is pi over 4 and 2. So x1 is pi over 4 and x2 is 2. And so then what we're going to get in general, the Jacobian is just going to be a matrix of numbers. In this case, it looks like this: 2.707, 2, 0.785, and 4.785. And again, you can refer to the book in example 6.1 if you want to read this again. But just to review what a Jacobian looks like. Okay, before we get into methods to compute derivatives, just going to give this kind of high-level overview of where we're going here. There are a few different ways we can look at our analysis, and we're going to use this version for today. This is what we call the black box version. It's a black box meaning we know that x goes in and f goes out, and we don't know or care about what's happening in between. All I know is that I've got some function, I'm going to give it an x, and it's going to return an f. And I can work with that. I can use that to estimate derivatives. Specifically with finite differencing, this is if this is what we have, then generally all I really can do is finite differencing. Sometimes we're lucky, depending on how the code was set up, we could do more. But if I don't have access to the source code, for example, say this is just a binary that I'm given, I may not be able to do much more. Another way we could look at our analysis is we could look at it line by line of code. Okay, and we could think about taking derivatives by thinking about it as a bunch of sequence of operations. We won't do that today, but that's another thing we could do. And obviously I need the source to be able to do that. A third option that's kind of in between those two, these are kind of the two extremes, like all I get is input and outputs. Here I look at every single line of code. In the middle, we think about solvers. We think about these as blocks. Inside each of the solvers, there's a bunch of stuff, a bunch of lines of code. We think about solvers and outputs of those solvers. This is kind of what we talked about with numerical methods, and that's something we'll talk about next week. Okay, but today we're going to take mostly the black box approach. We're actually we'll talk first about symbolic derivatives, and that's kind of in this area here. So before taking a derivative, let's just review an implicit function. Here's an example of an implicit function. This is motivated actually from Kepler's equation. Just put in some constants here, and it's an implicit equation. It's implicit, meaning I cannot explicitly solve for f. I cannot write f equals and then a bunch of stuff that don't contain x. F is on both sides, and I can't just move all the f's to one side and say f equals something. So it's an implicit equation. This occurs all the time in engineering. We had an example in my class last semester where we were analyzing a rocket, and we saw, for example, that let's say the tanks that are holding the fuel, the size or the mass of that tank depends on how much fuel I carry, right? If I've got more fuel, I need a bigger tank. But the amount of fuel I need depends on the size of the tank, because as that tank gets bigger, The rocket gets heavier, so I need more fuel. So I've got this coupled relationship. The mass of the fuel depends on the mass of the tank, but the mass of the tank depends on the mass of the fuel. That leads to this implicit relationship. I can't just explicitly solve and say the mass of fuel equals this. I need to do some sort of iteration or to solve this implicit equation. So this occurs a lot, and if you're not comfortable with this, I would review how you could solve this numerically. Say, for example, I told you that x equals 1. How would you solve for f? That would be a good practice to do on your own. There are many techniques you could do, ranging from simple things like fixed point iteration to Newton's method, which works in any dimension. Also for 1D in this case, there are specialized methods like bracketing methods and improvements on bracketing methods with interpolation that you could use to solve this. You could even do optimization. We could move everything to one side and do optimization, although that's not the most efficient approach. But that would be a good practice thing for you to do. In this case, what we're going to do is we're going to use fixed point iteration because it's simple. It's going to illustrate this idea of derivatives. So fixed point iteration just means the following, and you can't do this with every implicit function, but if it's a form like this, it works well. What it means is you give it a guess for f, and we just plug it in here. We know what x is. X is an input, right? And so it's f we're trying to solve for. I just guess f. I solve this, and I get a new f. And I take that new f, and I put it back over. Evaluate this again, I get a new f. And I just keep doing that, plugging it in, get a new f, plug it in, get a new f. And hopefully that converges. There might be multiple solutions, so it might depend on where I start. It might diverge, right? The same kind of problems we could have with Newton's method. But for this function, simple function, this should work pretty well. So here's what that would look like as an algorithm. Here we're doing that loop, right, where we're taking f is coming in, get a new f, and so that's going to be put in the next iteration. So we're just doing this loop, and we're just evaluating it over and over. We have to start with an initial guess for f. It could be anything. I could have put 1, 5, whatever, it doesn't matter. I just put x just for the purpose of this example here. Okay, so here's a very simple computational routine. It's hard to think of a simpler thing that, you know, is kind of a real engineering function. This is just a 1D type of thing here, but it has some iteration, so it's at least somewhat interesting. Now, in calculus, we spent a ton of time doing symbolic derivatives. Okay, so let's do that. That's something we could do. We could do symbolic derivatives. Let's think about what this looks like. So let's just say if I was equal to 1, say we only did one iteration, then we'd start with f equal to x. We'd have f equals the sine of 2x. And that's a super easy derivative to do, right? So at the end of the day, what I want is df dx, where the f I want is the f that comes out at the end of this whole algorithm. So x comes in, we do some stuff, f comes out. I want that derivative, df dx. If I equals 2, then it gets a little more complicated, right? So we start with f equal to x, we plug that in here. So we get we still have f as the sine of 2x, but on the next iteration, that gets plugged in here. So I get f is equal to the sine of x plus the sine of 2x. And then if I equals 3, then it becomes f equals the sine of x plus the sine of, I'm plugging that whole thing in, right? The sine of x plus the sine of 2x. And sorry, it's getting messy, but you can see this quickly becomes kind of long. And I can do this, right? Everything just depends on x here. Just apply the chain rule a bunch of times. You could do this. It's not very fun, but would rather just plug it into a computer and have it do it for us. So let's do if I equals 10. Actually, I think I did I equals 20. This is I equals 20. This is what it looks like. It's a horrible mess. I mean, it's just really long, but it's doable. I could copy and paste that and write a function around it. It's very inefficient. There's a lot of redundant calculations, and it kind of exploded. We call this expression swell. In fact, it starts growing, you know, like exponentially. If I put I equals, I can't remember, maybe like 60 or so, it just becomes way too big, pages and pages and pages and pages. So it becomes ridiculous. Whereas the original loop, evaluating this with 60, I mean, it's not a big deal at all, very fast. But the derivative just becomes crazy to do symbolically. So this highlights maybe our first challenge, is that symbolic differentiation doesn't actually usually play a very big role in optimization. There are some pieces usually within a function that we can do symbolically, and it works well. Especially maybe if our governing equations are PDEs and we can do some symbolic derivatives. But with these multidisciplinary engineering functions with lots going on, symbolic derivatives are just intractable. And even if we can do them, this is not very computation efficient. It's very slow. We're doing lots of just unnecessary calculations. So this is just, unfortunately, plays a limited role. So all those things you learn in calculus just won't really be used too much here if we're taking derivatives. Maybe that's a relief for you. I don't know, but it's just not as useful. Okay, so that's kind of this model where we could look at the lines of code. We'll go back and look at some better ways to do this later this week. But let's go back and think about this black box model. I don't know nothing about what's in there. I don't really care. Here's something where we can do finite differencing. You've probably heard of finite differencing, maybe used it. I'm going to derive it first for you, and then and then we'll look at how maybe some examples. You've seen this before, just maybe from calculus, but let's start maybe more rigorously from like a Taylor series. The idea is, well, we've done the Taylor series a bunch of times already. Let's just do it in 1D first. Let's say I'm taking some small step h. H is something we're going to use for a step size. I'm just going to start with a 1D function first. Let's say I want to expand this into a Taylor series. I'm going to get f of x plus that step size, usually we'd call that delta x maybe in calculus, times the partial, or it's actually a total derivative since I'm just doing 1D first. Let's call it f prime of x plus h squared over 2 times f double prime of x, and so on. And I'm interested in a way to estimate the derivative. So what I'm going to do is I'm going to get rid of all these higher order terms. I'm just going to ignore them. I'm going to solve for f prime of x. So I get f of x plus h. I'm going to do this in one step. Hopefully that's okay. Minus f of x divided by h. Right, and this is like, I don't know, is this the first fundamental theorem? It's one of the fundamental theorems of calculus, right? This becomes a definition of the derivative in the limit that h goes to 0, right? Of course, we can't actually do that limit, but so in our case, it becomes an approximation to that derivative. So let's see that, and then I'm going to go back and do that in ND. Here's just a pictorial example of that. Here's, for example, gray here is my actual curve. And the blue line, that's the tangent line. That's the slope at that point. That's the actual derivative. I'm going to estimate it with finite differencing. So I evaluate f at some x. I evaluate at some nearby point, right? And I'm basically fitting this line. And the slope, the change in f over the change in x, that's what this equation is, change in f over the change in x. That's my estimate for the derivative. It's a finite difference. And as h gets smaller, as calculus tells us in the limit as h goes to 0, I would get back my true derivative. So this is a way we could numerically estimate a derivative. I don't need to know anything about what's going inside. All I have to do is be able to evaluate f, which I always have to be able to do. So I give you an x, you give me back an f. I give you another x, you give me back another f. I take a difference between these two, divide by h. I have an estimate for the derivative. That's great. Many optimization packages will do this by default because, again, we don't have to know anything about your algorithm, so we can write a very simple function that will work for any, or finite differencing function that would work for any input. You could give me any function, just a black box. I just sample it at nearby points, so I can estimate derivatives for you without knowing anything about your function. And so, like I said, that's a default in many optimization packages that if you don't provide derivatives, it will finite difference them as an estimate. Now, the same thing works in higher dimensions. So in general, remember, x is going to be a vector, right? So if it's a vector, then the same thing works. The Taylor series is going to be like f of x plus h, but we're going to take a step in the jth direction. Okay, so that would look like, let's say you'd add a column vector of a bunch of zeros, and then the jth entry would have an h. So we're only adding a step in one of those dimensions. But the Taylor series is going to be f of x plus h times the first derivative, but it's, since I have many x's, it's just a partial derivative with respect to that j, plus the higher order terms. And so my derivative becomes the partial of with respect to xj, or sorry, the estimate of that derivative is f of x plus h in that one direction minus f of x divided by h. Okay, and we say in both cases, I probably should have wrote these are order h, meaning this is the error that we have. We got rid of second order terms. So this is a first order method. Our truncation error is proportional to h. So meaning the smaller I can get that step size, my error is going to decrease proportional to that step size. If we were to go back and look at the Jacobian, notice that I have to do this once for each x. I can do this one x at a time, but I get all of my f's at once. So when I do a finite difference, if we were to look back at this Jacobian here, sorry, I'm going all the way back. I'm basically getting a column of this Jacobian at a time. So I do a step in one x direction, I get this column, and then I do a step in another x, I get another column, and so on. So this is one of the downsides of finite differencing, or maybe not a downside, depends on what you've got, but this is a limitation to keep in mind. I have to do this nx times. So as my number of design variables grows bigger, I have to do this extra evaluation for every dimension. So if I was doing this forward difference, if I had 100 inputs, I would need to evaluate my function plus my function at a nearby point 100 times, right? Because I'm taking a step in each dimension. So this can become very costly as my dimensionality grows. Okay. Well, let's see. Yeah, before I, okay, let's talk about central difference while I'm on it. I'll just do the same example here. So for central difference, it's the same idea. We're going to do that Taylor series. Here, I'm going to take it in a jth direction, for example. I get f of x plus h times the first derivative, and then I get my second derivative terms. I'll keep them this time. Second derivative over 2, and then I get higher order terms that I'm going to neglect. I'm now going to do the same thing, but I'm going to take a step in the minus direction. Okay, so everything's going to look exactly the same except for all my h's become minus h's. So this is the same except for the minus sign. A minus h is going to look the same because a minus h quantity squared is going to give me a positive value. So this term is going to be exactly the same. And then this third order term would be a minus sign. So what I'm going to do is I'm going to neglect all these higher order terms. I'm going to take this expression here and subtract the next one. So I get, notice that this is going to now cancel, and this is going to cancel. So I have f of x plus h minus f of x minus h equals h squared times, not h squared, sorry. I was looking at the wrong row there. Let's see, I've got an h minus an h, that gives me 2h partial of f with respect to xj, if I did that right. And so now I can solve an estimate for my derivative. It is f at x plus h minus f of x minus h divided by the step length. So it's the same idea if we were to go back here, except for I took a, well, let's just draw it here. Let's say this is my curve, something like this. And instead of taking a one-sided difference, here is x. I'm going to take a step h and a step minus h, right? And I'm going to then fit a line between those 2 points there. And that's in general going to give me a more accurate derivative, because I'm not just stepping on one side, I'm stepping both sides. And we see that because the error term here, we didn't actually have to get rid of the second order term, whereas before we had to get rid of that to get our derivative function. Here, those happen to cancel. So my error term is of order h squared. So that means my error is going to decrease faster as I make smaller step sizes. So this is what we call central difference. The downside of this compared to forward difference is I now need to see in 1D, I evaluated my function and then one more. With central difference, I got to evaluate my function because I always need my function. But for the derivative, I have to evaluate 2 points, right? One on each side. And in n dimensions, right, with x's, I've got nx values, I have to do 2 times nx function evaluation. So twice as many as the forward diff. I get a bit more accuracy, but it takes twice as many calculations or function calls. And this can be prohibitive. Both of these can be prohibitive as nx becomes large, especially when my engineering simulation is expensive. Okay, so let's do an example real quick. I'd encourage you to try this on your own, but let me talk you through this first. So here's a function, just a simple 1D function. It's not an implicit. The implicit function I showed at the beginning, you could actually do that with finite differencing really easy. And I encourage you to try that. But let's do something explicit here, really simple. This is something we can solve for symbolically, and this is the exact answer to 16 significant figures, 16 digits here at x equals 2. So I encourage you to try this. Try to do a forward diff and experiment with the step sizes. If you haven't done this, I encourage you to pause and try it. I'm going to do it for you. All right, so actually I'm going to switch what I'm sharing here. Let's just jump over to a terminal. We could do this in MATLAB or whatever, but it's going to be easy for me to just do this quickly here in a terminal. So it's actually in Julia, but you don't need to know any Julia to understand this example. So I'm going to write that function. This is the function I just said. It was the square root of sine of x cubed plus the cosine of x cubed. And yeah, I think that was the function. Okay, so there's my function. And I could evaluate my function x equals 2, for example. That's great. So I want to evaluate a derivative. So let's try to choose a step size. Let's say x equals 2. And let's pick a step size. Remember that h. Let's try something like 1e to the minus 2. So remember our formula is going to be the function at x plus h minus the function at x all divided by h. So that's an estimate for my derivative. It's 19.3032. The exact derivative was this. This is the exact derivative. And so I'm just going to write it exactly. Let's just call this df. Just save it. Okay, so that's not very good. But remember, as we talked about, my error is proportional to h. And the fundamental theorem of calculus tells me I should go to h equals 0. So the smaller and smaller I make the step size, I should expect more accuracy. Let's go to, like, say, just jump down to 1e to the minus 6. Okay, and then do that estimate again. That's looking better. Right? If we compare to df, we can see I've got 4 digits. So two decimal places here, 4 digits. That's getting good. Maybe 5, I guess you could say. So maybe we should go smaller. Let's go 1e to the minus 8. And again, let's put the exact. I'm getting a few more digits. 7, 8, maybe 9. Yeah, so about half of the digits. It's pretty good. So let's keep going smaller. And we compare these. And now I've got actually less. I've got like 7 digits. Okay, so that might be an aberration. Let's just go smaller. And if we compare to DF, it's getting worse. I have fewer digits. Let's just keep going. Minus 14. Now I can clearly see that that's not good. I think it's getting pretty far off. And I can go smaller. And now it says my derivative is 0. So what's going on, right? We thought that h should become smaller and smaller, and that'd be better, but this is getting worse. Well, the problem is I have finite precision arithmetic. This is what we discussed in the numerical models section. If I had an infinite number of digits on my computer, this would indeed work, right? I have more and more digits. I can keep taking more and more differences, but look in this last case, function, evaluate these 2 points, these are identical. So when I subtract them, I get 0. Now they do differ, right? But they differ here in these digits that don't exist for me. I don't have that many digits of significance, so I can't resolve them. Let's do h equals 1 to the minus 14. Oops. And evaluate those 2 functions. This is the problem that we refer to as subtractive cancellation. Notice that these digits all the way to here agree, and I differ here at these last few digits, 4 digits in this case. So I've lost, when I subtract those 2 numbers, I only have 4 significant digits. All the other numbers are just garbage, and so I'm getting inaccurate derivatives. So I've got this problem where I want to take smaller and smaller step sizes to bring my error down, but if I take smaller and smaller step sizes, at some point I'm going to be losing digits due to subtractive cancellation. I'm going to jump back over to the other screen. So this is a real challenge of finite differencing, and in fact, it may not seem that big of a deal. Like I can get, maybe 6, 7. In practice, you usually can get maybe about 6 digits of accuracy, maybe 8. For simple models, you can get more, maybe like 8, like we saw here. But with complex engineering models, with iteration and such, 6 is maybe more typical, but it'll vary. That sounds like pretty good, but that's not really great, right? Like your original function, you have maybe, potentially 16, probably in practice, maybe more like 14, 15 significant figures. And now from finite differencing, we've lost about half of our digits. That can affect the many of our methods. We have way less accuracy. So here again, this is that example of subtractive differences, right? Where all these digits agree except for the last 2. So when we subtract them, we've lost so much information. So we have this problem again. We need small steps in order to get to decrease our truncation error. The fact that we took a Taylor series and didn't include all those terms, but on a computer, we're going to get subtractive cancellation. So in theory, the optimal step size, with some certain assumptions, for this forward difference is about the square root of epsilon, where epsilon is the machine precision. So say you could get to, say, 10 to the minus 14. That would mean that the accurate, or the optimal step size would be about 10 to the minus 7. We usually don't have quite that many digits of precision. So usually an optimal step size is around 10 to the minus 6, maybe 10 to the minus 7. It really depends. Usually some testing is required. And it also says that the error bound is also the square root of epsilon, meaning that you'd get about 7 digits of accuracy, if you had 14 digits of accuracy in the first place. So basically, you lose half the digits of accuracy. Central difference does a bit better. The optimal step size is about epsilon to the 1/3, and the error is about epsilon to the 2/3. So that means, let's say I had only 12 digits of accuracy to make the math a little easier. With 12 digits of accuracy, I would get an optimal step size of 10 to the minus 4, so bigger step size than forward difference, and I'd get about 8 digits of accuracy. Notice that I would have expected to get more than that, because with the forward difference, we said we got 6 digits of accuracy. So with a second order method, I should have got double that. I should have got 12 digits of accuracy, but I only get 8. And that's again because of that finite precision arithmetic. So central difference will improve things, but it doesn't improve it quite at the rate that we had hoped. We'll see that again next time. We'll kind of review this. I'll show you a plot, but I think this is good for today. So next time we'll kind of review this a little bit, look at forward difference and central difference, and we'll look at some other ways we can address this. So to recap, finite difference, it's a useful method because it can work with this black box models. We don't have to know anything about the function. We don't have to have the source code. It can be just a binary, and we can still estimate derivatives. But it assumes, that the models in there have been are smooth, right? That we took good care to write good models that are not going to produce this noisy output. That are not going to have these discontinuities and things that we produced good outputs. But if that's the case, we can provide derivatives. But the limitations is that we have to evaluate just to get one Jacobian, right? At each iteration, right? We want a Jacobian. We have to evaluate our function nx times, or 2 times nx if we want to do essential difference. That can get expensive, especially if our, depending on how expensive our function is. Also, we lose about half our digits of precision. So our derivatives are actually not super accurate. So we're going to look at other methods where we can try to improve on some of these, where we can get accurate derivatives and potentially get them more efficiently. We'll see you next time.